Ladies and gentlemen, thank you for joining me on this intellectual journey through the remarkable world of geology and its literature. Today, I present to you the story of how geology, one of the oldest sciences, evolved over thousands of years, and how the books that shaped it guided generations of curious minds, explorers, and scholars. Let us begin where all stories begin, in the distant past, long before the word geology was even coined. Geology, our scientific study of the Earth, its structure, its materials, and its history, has roots that stretch far into human prehistory. Long before we had the tools of science, ancient civilizations were already observing the rocks beneath their feet, the mountains on their horizons, and the strange fossils embedded in stone. Their understanding may have been primitive, but their curiosity was profound. The ancient Egyptians, for example, understood rocks not as objects of scientific analysis, but as symbols of power and eternity. They quarried granite and limestone for their temples and tombs, choosing materials based on their durability and appearance. The pyramids themselves are monumental geological achievements, though created without the formal knowledge we possess today. Similarly, the Babylonians and Chinese kept records of earthquakes, volcanic eruptions, and river floods. They may not have known the mechanisms behind these events, but they recognized patterns. These early observations were the first glimmers of what would later become geological science. But it was in ancient Greece that we see the first attempts to truly understand the Earth through natural philosophy. Thinkers like Thales of Miletus, Anaximander, and Aristotle tried to explain natural phenomena without relying on mythology. Aristotle, in particular, wrote about the Earth's internal processes, speculating on erosion, sedimentation, and even the formation of fossils. Even though their explanations were often inaccurate, their approach was revolutionary. They asked why and how, rather than simply accepting what is. This shift from myth to reason was a turning point for science. By the time of the Roman Empire, scholars like Pliny the Elder had begun cataloging natural materials, including minerals and stones. His book, Naturalis Historia, was a massive encyclopedic work covering everything from astronomy to geology. Though not scientific by today's standards, it represented an important step forward, a desire to gather, organize, and transmit knowledge about the natural world. Fast forward to the Islamic Golden Age, and we find even more progress. Scholars like al-Biruni in the 11th century measured the Earth's radius with astonishing accuracy. He also studied fossils and sedimentary layers, proposing that parts of the Earth had once been underwater. Again, we see a move toward empirical observation, an essential building block of modern science. Yet despite these early contributions, geology remained fragmented. It was a patchwork of observations and philosophical musings, lacking the structure and evidence-based methodology we now associate with scientific disciplines. What held geology back for so long? Two things: the dominance of religious cosmologies and the absence of a unifying theory. For centuries, people believed that the Earth was created in its present form and remained unchanged. The idea that mountains could rise or that continents could drift was inconceivable to most. But change was coming. By the time the Renaissance swept through Europe in the 15th and 16th centuries, a renewed interest in observation and experimentation began to stir. Artists like Leonardo da Vinci studied rock layers and fossils, correctly interpreting them as the remains of ancient life. not curiosities or tricks of the devil, as others claimed. This period laid the groundwork for geology to emerge as a true science. Still, it would take several more centuries for the field to gain clarity, direction, and structure. And that is where our story leads next. I will take you into the age of the great pioneers, those brave minds who dared to look deeper, dig further, and think differently. People who didn't just observe the earth, but sought to explain it through reason and evidence. They didn't only change science, they wrote the first pages of geology's book. As we continue our journey through the evolution of geology and its literature, we now arrive at a transformative period, the era of the pioneers of geology, the courageous minds who began turning scattered ideas into a structured science. This was the beginning of geology as an independent discipline, shaped by observation, evidence, and, importantly, writing. In the early 17th and 18th centuries, a new attitude toward the earth began to form. Rather than accepting religious or mythical explanations for Earth's features, scholars started to ask, what can rocks tell us about the past? What processes shape the mountains, valleys, and fossils we see today? One of the first major contributors to this new way of thinking was Georgius Agricola, often called the father of mineralogy. Born in 1494 in what is now Germany, Agricola was not a geologist in the modern sense, but his work was foundational. His book, De Re Metallica, published posthumously in 1556, was one of the earliest detailed studies of mining, metals, and mineral deposits. Though his focus was on practical mining techniques, Agricola made groundbreaking observations about the nature of rocks and minerals. He described how different layers of the earth contained different ores, and he hinted at the idea that Earth's processes could be studied systematically. His work combined empirical data with illustrations and careful descriptions, key elements that would become standard in geological literature. But geology still lacked a coherent theory of how Earth's features formed over time. That began to change in the 17th century with the work of Nicholas Steno, a Danish scientist who is considered one of the founders of stratigraphy, the study of rock layers. In 1669, Steno published De Solido Intrasolidum Naturalita Contento, in which he laid out his famous principles of stratigraphy, including the law of superposition, the idea that in undisturbed layers of rock, the oldest layers are at the bottom and the youngest at the top. He also proposed that fossils were the remains of ancient organisms buried and preserved in sedimentary layers. Steno's principles were revolutionary because they introduced the idea that rocks and fossils recorded Earth's history in layers, much like pages in a book. This concept was a massive leap forward and would influence generations of geologists. Fast forward to the 18th century, and we find a man whom many regard as the father of modern geology, James Hutton, a Scottish geologist, farmer, and thinker. Hutton's work was truly groundbreaking. In the late 1700s, he proposed a theory known as uniformitarianism, the idea that the geological processes we see happening today, like erosion and sedimentation, have been shaping the earth for millions of years in a slow, continuous cycle. This idea directly challenged the dominant belief of the time that Earth had been shaped by a few catastrophic events, as described in religious texts. In 1795, Hutton published his major work, Theory of the Earth, in which he presented evidence from rock formations, landscapes, and erosion patterns to support his view. He famously declared that he saw no vestige of a beginning, no prospect of an end, implying that Earth's history was vast and ancient, far older than anyone had previously imagined. Though Hutton's writing was complex and hard to read, his ideas were so powerful that others soon took up his cause. One of these people was John Playfair, who rewrote Hutton's ideas in a clearer form, helping them gain traction in the scientific community. Then came William Smith, another pivotal figure in geology's rise. Born in 1769, Smith was a humble canal surveyor in England who made one of the most important discoveries in geological history, that rock layers, strata, could be identified and correlated based on the fossils they contained. Smith's creation of the first geological map of England in 1815 was a monumental achievement. It showed how different rock layers were distributed across the country and how they related to one another. His map was the first of its kind and laid the foundation for modern geological mapping. Smith also compiled fossil records and noticed that certain types of fossils always appeared in the same order in the strata. This principle of faunal succession became a powerful tool for dating rock layers and reconstructing Earth's past. Now, you may be wondering, who wrote the first book that could truly be called a geology textbook? That distinction often goes to Charles Lyell, who in the early 19th century published Principles of Geology. This book, released in 3 volumes between 1830 and 1833, brought Hutton's ideas into the spotlight, but in a much clearer, more readable style. Lyell's work explained geological concepts using real-world examples and emphasized that the same slow processes we see today, like the formation of river valleys or the uplifting of mountains, were responsible for shaping the ear. Principles of Geology became the most influential geology book of the 19th century. It was so powerful, in fact, that a young naturalist named Charles Darwin took it on his famous voyage aboard the HMS Beagle. The book deeply influenced Darwin's thinking about change over time, ideas that would later form the foundation of his theory of evolution. So, to summarize this important phase in geology's evolution, Agricola laid the foundation with detailed descriptions of minerals and mining. Steno introduced the idea of Earth's history recorded in rock layers. Hutton proposed uniformitarianism, suggesting Earth is shaped by slow, continuous processes. Smith created the first geological map and pioneered the use of fossils to date rocks. Lyell communicated these revolutionary ideas through one of the first true geology books. These pioneers not only transformed how we see the Earth, they showed us that rocks are not just dead matter. They are living records of a planet that is constantly changing layer by layer, year by year, over the course of deep time. And how did these ideas spread? Through books, through the written word, through the careful recording of observations, theories, and maps. Ladies and gentlemen, we have now arrived at one of the most exhilarating periods in the history of geology, a time of bold exploration, heated debates, and groundbreaking discoveries. The 18th and 19th centuries witnessed a scientific awakening, not just in geology, but across all the natural sciences. Geology, in particular, experienced a transformation from a collection of scattered observations into a structured and respected scientific discipline. This era laid the foundations upon which modern geology is built. Let us begin by revisiting the ideas that dominated scientific thought in the early 18th century. Two schools of thought stood in stark opposition to each other: Neptunism and Plutonism. The Neptunists, led by Abraham Gottlob Werner, believed that all rocks were formed from the crystallization of minerals in a vast ancient ocean. Werner's theories were elegant and deeply influential, especially in Europe. His ideas categorized rocks by their age and appearance, with older rocks supposedly having formed when the oceans were at their highest levels. However, there was a flaw. His system lacked a satisfactory explanation for volcanic rocks like basalt, which clearly did not form in water. On the other side were the Plutonists, most notably James Hutton, whose ideas we discussed in the last part. Hutton argued that rocks could also form from molten material, and that Earth's internal heat played a crucial role in shaping its surface. His theory introduced the concept of deep time, a revolutionary idea that Earth's processes required millions of years, not just a few thousand. This intellectual battle between Neptunism and Plutonism drove the geological community to look more deeply at evidence in the field. Geologists were no longer content to theorize from their studies. They began exploring mountains, coastlines, quarries, and valleys to examine Earth's layers firsthand. One of the most influential figures of this time was Charles Lyell, whose principles of geology made uniformitarianism, the idea that the present is the key to the past, the central philosophy of the science. Lyell's clear writing, filled with real-world examples, brought geology to life. His book popularized the concept that geological processes like erosion, sedimentation, and volcanic activity occurred gradually over vast stretches of time. His ideas directly influenced young scientists like Charles Darwin, who read Lyell's work while on his voyage aboard the HMS Beagle. It's important to understand that geology wasn't just a theoretical science. It became an exploratory one. During the 19th century, geological expeditions began mapping the Earth's surface in unprecedented detail. Governments and scientific institutions funded massive projects to chart rock formations, fossil records, and mineral deposits. The first geological surveys were born in this era, leading to the creation of national geological maps that are still in use today. Let us not forget William Smith, the father of English geology, who created the first National Geological Map of England in 1815. His use of fossils as markers to correlate rock layers across different regions was nothing short of revolutionary. Smith's fossil-based stratigraphy showed that the same types of rocks and fossils could be found in predictable sequences, regardless of location. This principle, called faunal succession, became a key tool for understanding Earth's history. As fieldwork advanced, another crucial area of geology was developing: paleontology. Scientists began to study fossils not merely as curiosities, but as records of ancient life. Fossils helped geologists piece together Earth's biological history and recognize mass extinctions, evolutionary changes, and environmental shifts across geological time periods. The 19th century also saw the first attempts at geological timescales. Scientists began to divide Earth's history into eras, periods, and epochs based on the types of rocks and fossils they discovered. Terms like Paleozoic, Mesozoic, and Cenozoic entered the geological vocabulary. These names, still used today, represent vast chapters in Earth's story. During this time, The scientific method was becoming more deeply embedded in geology. No longer was the field dominated by speculation. Instead, hypotheses were tested through observation, experimentation, and comparison. Laboratory work emerged alongside field work, and geology began to take its place among the hard sciences. At the same time, geology was spreading into industry and education. The Industrial Revolution drove demand for coal, iron, and other minerals, and geologists were called upon to locate and assess mineral resources. This gave rise to economic geology, which connected academic study with real-world applications. Geology was no longer just about understanding the Earth. It was about using that understanding to fuel progress. And as the science evolved, so too did its literature. Geologists began publishing books, field notes, reports, and maps with increasing frequency. Professional journals like the Geological Society of London's Transactions, established in 1807, created platforms for sharing discoveries and debating ideas. These journals became critical in shaping geological thought and maintaining scientific standards. In classrooms, geology became a subject in its own right. Universities established geology departments, and the first textbooks for students began to emerge. These early academic books, built on the work of Hutton, Lyell, Smith, and others, organizing Earth story into chapters that could be taught, studied, and questioned. To summarize, the 18th and 19th centuries brought the clash of Neptunism and Plutonism, pushing geologists toward deeper inquiry, the rise of field-based research and national geological mapping, the discovery of faunal succession and the development of stratigraphy, the birth of paleontology and geological timescales, the expansion of geology into industry, academia, and formal literature. It was a golden age of discovery, one that laid the structural and intellectual framework for everything that followed. And crucially, it was the period in which geology truly became a science of history, not just of rocks, but of the Earth itself. We now move into one of the most transformative eras in the history of geology, the 20th century. This was not just a time of scientific growth. It was a revolution, a period when long-standing mysteries were solved, new tools transformed exploration, and geology evolved from descriptive science into a highly technical, interdisciplinary field. In earlier centuries, geology had revealed that Earth was ancient, that layers of rock held records of the past, and that fossils could be used to trace life's evolution. Yet despite all these discoveries, one fundamental question remained unanswered. How did continents and oceans come to be where they are? This mystery puzzled scientists for centuries. Some had noted that the coastlines of continents, like South America and Africa, seemed to fit together like puzzle pieces. But few dared suggest that continents might have once been joined and then drifted apart. That idea, to many, sounded like fantasy. But in 1912, a German meteorologist named Alfred Wegener proposed a radical theory, continental drift. Wegener suggested that all continents had once been part of a single supercontinent he called Pangaea, which gradually broke apart. He pointed to fossil similarities, rock formations, and ancient climate evidence found on widely separated continents to support his idea. However, he couldn't explain how the continents moved. Lacking a mechanism, his theory was largely rejected by the geological community at the time. And yet, Wegener had planted a seed. Over the following decades, especially after World War II, new technologies began to emerge that would change everything. Sonar mapping of the ocean floor, developed during wartime submarine tracking, revealed vast underwater mountain chains known as mid-ocean ridges. These ridges weren't just geographic features, they were geologically active. By the 1950s and 60s, geologists like Harry Hess and Robert Dietz expanded upon Wegener's theory with a new concept called seafloor spreading. They proposed that new crust was being created at mid-ocean ridges and pushed outward, moving the continents apart. This idea finally gave Wegener's theory the mechanism it needed, the movement of the Earth's lithospheric plates. All of these ideas came together in what we now know as the theory of plate tectonics. This was the great unifying theory of geology, the idea that Earth's outer shell is divided into tectonic plates that float atop a semi-fluid layer of mantle. These plates move slowly but constantly, colliding to form mountains, sliding past one another to cause earthquakes, or diverging to create new crust. By the late 1960s, the theory of plate tectonics had become widely accepted. It provided a single, elegant framework to explain an enormous range of geological phenomena: the formation of mountains, like the Himalayas, the origin of ocean trenches and volcanic arcs, the distribution of earthquakes and volcanoes along plate boundaries, the movement and collision of continents over geological time. Plate tectonics revolutionized not just geology, but also our understanding of Earth's dynamic nature. For the first time, geology had a global theory, one that could explain the past and predict the future movements of our planet. As this theoretical revolution unfolded, so too did a technological one. The 20th century saw the birth and growth of geophysics, geochemistry, and remote sensing, which gave geologists entirely new ways of looking at the Earth. Let me give you some examples. Radiometric dating. Thanks to advances in chemistry and physics, scientists could now determine the exact age of rocks and fossils using isotopic methods. This allowed geologists to build a precise geologic time scale, revealing that Earth is approximately 4.54 billion years old. Seismic studies. Using data from earthquakes, scientists mapped the interior of the Earth. They discovered the layered structure, crust, mantle, outer core, and inner core, and learned how seismic waves change as they pass through different materials, satellite imaging, and GPS. These tools allowed geologists to track plate movements in real time and study Earth's surface with unprecedented accuracy. Computational models. With the rise of computers, geologists began simulating Earth processes such as climate change, mantle convection, and ocean circulation, offering new insights into past and future planetary behavior. As geology embraced these tools, it also became increasingly interdisciplinary. It merged with physics, biology, chemistry, and even astronomy. New branches of geology emerged: volcanology, paleoclimatology, planetary geology, hydrogeology, and environmental geology, just to name a few. Let's not forget how geology expanded its practical applications in this era. In the petroleum and mining industries, geology played a critical role in locating and extracting natural resources. In civil engineering, geologists advised on the stability of foundations, tunnels, and dams. In natural disaster risk management, geological studies helped governments and communities prepare for earthquakes, tsunamis, and landslides. In space exploration, Geologists helped analyze lunar and Martian rock samples, pushing the boundaries of Earth-based geology into the solar system. At the same time, geology became more deeply embedded in education. Universities around the world established strong geology departments. Students were trained not only in classical fieldwork, but also in laboratory techniques, data analysis, and computational modeling. Textbooks evolved rapidly, becoming more visual, data-rich, and specialized. Titles like Earth, Physical Geology, and Understanding Earth became academic staples. And what of geology books during this era? This century saw a boom in scientific publishing. New journals were founded like Geology, Journal of Geophysical Research, and Earth and Planetary Science Letters. Scientific books became more specialized, with entire volumes dedicated to sedimentology, tectonics, paleontology, and more. Geology became a science of depth and specialization, and its books reflected that. In short, the 20th century brought the revolutionary theory of plate tectonics, the integration of advanced technologies, the rise of interdisciplinary approaches, the professionalization and specialization of the field, the explosion of geological literature and academic education. Geology had come a long way from the days of guessing at the origin of mountains and collecting fossils out of curiosity. It had become a robust science, a career path, a tool for resource management, and a guardian of environmental and planetary understanding. Photograph fossils and contribute to global geological databases. This democratization of science empowers communities and enriches data collection. But amidst all this progress, challenges remain. Our planet is under pressure. Melting glaciers, rising sea levels, resource scarcity, and habitat destruction all pose serious threats. Geologists are increasingly being called upon to inform policy, guide sustainable development, and engage with the public. This has led to a growing emphasis on ethical and sustainable geology. Mining operations are now evaluated not just by their profitability, but also by their environmental footprint. Geologists are trained to think about how their work affects communities, ecosystems, and future generations. The 21st century geologist is not just a scientist, they are also a communicator, a policy advisor, an educator, and an environmental steward. Let me highlight some key themes of this era. Geology in service to the environment and society. Digital tools transforming every aspect of the field.